So, okay, we're going to analyze a grate inlet in the sag. And the discharge to the inlet was computer. Well, don't worry about that. The street was designed using a sag vertical curve with a low point at inlet 1. A storm drain system will be designed to carry collected runoff away from the area. We're not actually going to design a storm system, but we are given, the grade is a P50 times 100. It's 2 by 2 feet, 2 foot wide gutter and a half-foot high curb. Cross slope is 2. This is a composite section, so the gutter cross slope is a 12-to-1 ratio. Local criteria required that the 10-year runoff in the gutter not overtop that curb and not exceed 1/2 of the outside driving lane. So we have a Q10 of 1.74 CFS and a Q100 of 11. So you are to find the hydraulic capacity of the inlet at the maximum curb depth of 1/2 foot. And then if the inlet is sufficient to intercept the 10-year runoff without exceeding the allowable spread, figure that out. And then you'll look at how much ponding is going to occur with a 100-year storm. So we gave you some equations you can use there. And go through it.
Not use a lot of different spreads. Yeah, that's the big thing.
Okay, let's go through it, okay, folks?
Sure. That's a great
So
idea.
for
Kids know about it, so I'll assume I would.
problem A, number 1, we're supposed to establish the capacity of the grade at the water depth at the top of the curb. So we know that the top of the curb is at 0.5 feet, right? And from chart 9B, we know we have to have our perimeter. So our perimeter is 6 feet, right? So, sorry. So at the top, we know that we are in near flow. That was given to you, unfortunately. So then we're going to establish the discharge, and remember that the depth at the top at the curb is not the depth to use in the equation. You have to average the depth across the grate, right? So you use the equation that I put up here, D equals D2, which is at the top of the curve, minus SW times W divided by 2. And you get 0.42 feet. Okay, that's at the top of the curve. And then we can use equation 4.26, and that is the interception is equal to, this is the Weir flow equation. It's CW times the perimeter times the depth, and you get 4.9 CFS, okay? Then if we go to the second question, we want to check to see if the grade has the capacity to intercept a 10-year runoff and not exceed the allowable flow, allowable width of spread of 1/2 of the traffic lane plus the gutter width, right? So we can use the equation and the discharge of 1.74 to determine the flow depth and the width of the spread. So what did you find for that depth? 0.21. That's right. Okay.
Oh, that's the average depth.
Okay. And so, yeah, that's the average spread. So now you have to find the D1, which is D2, which is the 0.05. I'm sorry, the 0.21 minus that composite section. And you get 0.13, right?
Yes.
I'll let people write that down before I go on. So at this depth, the spread on the pavement T is equal to the W plus the spread in the road, basically T sub S. So what'd you get for that? Anyone? Anybody calculate a spread there? So if the T now is 2 at the gutter, and to find the width, you can take the D divided by SX, and you get, 6.5. So we have a spread of 8.5. Because remember, D equals T times SX. So if you rearrange that, you can find the D. And so it's D divided by SX.
Wait a minute. So wait, the average depth, so the average depth becomes a D2 in that equation there?
Should be D1, right?
D1.
You know, the D1 equals D2, but you replace D2 with the average depth.
Right.
D2, yeah. I gotta look at a rule here.
Should be like 0.29.
D1 is equal to D minus, yeah, so D, your average depth, minus the composite.
Here, D1 and D2 are backwards.
The D2
Because D2 is the total. Yeah, then you need that to get how wide it's going to spread out into the window.
This is great.
The D2 was 0.29 and then D1
So let me ask you, how does this compare with the allowable spread?
It's too much.
It's too wide, isn't it? Yeah, because our allowable spread is 8 feet. So the two pieces. This is coming from somewhere else. Oh, let's see. So the ponding, unfortunately, I don't have that here.
I'm gonna assume this is too much.
So to do the ponding, and you had 11 CFS. So first you want to find your P, then you find your A, which times that clear opening area, which is 3.2, and then you can go into the chart. 9B. What did I do with my 9B?
And she took the unaverage of that. She unaveraged this.
So with,
These are.
I'll get myself okay. So we had a perimeter of 6 feet and an area of 2 by 2 times that 0.8 for the clear opening. So our area equals 3.2. So we can go into the chart and we don't have a line to subtract. So we made our own. Okay. And you can see from this chart in, so what was our depth? Flow depth was
If you
about
were adding to your depth, then you'd be going away from where it changes into the gutter section.
here.
You want to go from your average towards where the street becomes a gutter.
Actually, it's down here somewhere.
If you're going deeper, you're going the wrong way.
And that's because
I feel like she's got You're trying to find.
So chart 9B gives average flow depth.
this depth right here.
Well, yes.
Okay, okay, so that was part
In
of
this
my
case, we're finding this depth.
So, the grates in the transitional zone
You could
between
also,
wear and orifice
if you
control.
found this depth,
Okay.
then you have this.
So the D average is equal to
It's-
D2 minus SW times W. And so if we work that out, we get 0.72, and here's what's going on. Here's your section, here's your SX, your SW. D2 is up to the top of the curve, D1 is the D for your, at the end of your pavement. Yeah,
So,
so you know it's 0.72 is D2 plus this, and the answer for D2 is 0.8. You can work it out. Because we came in here, we're at 3.2, and we gotta go down to about 11, which CFS, which is somewhere in here. Say that's 11, so we bring it on up to our 3.2. We had to make this line from P6 to 3.2 connect, and if we do that and come on over, we're somewhere around 0.72. That's how we're getting that depth. Once we have that, then we can put that 0.72 into our equation, work it out, and we get that D2 is equal to 0.8.
yeah, okay. Okay, I was confused because I thought the chart was giving the highest D and not the average. Okay.
Yeah, and I was just confused there for a while myself.
Yeah, there's D1, D2, and D. We'll walk on that.
One more detail.
So if the curb height is at 0.5 and our D2 is at 0.8, what's going to happen? Yeah, the whole thing is flooded, right? The whole thing is flooded. It went over the curb and it's over everywhere. So thanks for persevering. So you know what, we're running out of time, so let's just, I will just go through these next ones with you. And I'll give you the answers, so you can write them down and look at them later, okay? So if we analyze a grade on a grade with a uniform cross slope, that's our next one. And so, the next concept, we're going to review an inlet on grade with a uniform cross slope, such as inlets 2 or 3 in the segment. Don't worry about that. So they have it given. Our cross slope is 0.02 right here. Grade type is the same, that P50 times 100, 2 by 2. Curb height is 1/2 foot. Curb gutter width is 2 feet. Cross slope is 2, so that longitudinal is 1, and our spread is 8 feet. So we're supposed to find the intersection capacity of the grade. And you can see that we have given you these equations to help us do that. So what we're going to do, we know our gutter capacity is 1.31 and our gutter velocity is 2.05. We found that in other problems. So for a 2-foot long grade, our gutter flow ratio is that, we have it here, gutter flow ratio. Anyway, it's 1 minus 1 minus, the quantity 1 minus width over T, W over T to the 2.67. So we can say it's 0.54, right? Any questions? From chart RF, for RF from chart 5B, see if I can bring that up. RF equals 1. And why is that? So we are 131 length of the grade What's the length of our grade? Is it 2? It's 2.
Yeah, that's it.
So we come in here to 2, and we got a P50 times 100, which is this 1-70. We come up here, and we can come across, and what was our velocity? What's that?
It's the 170
178 dash, well, it's a 178, so that's the same. We don't, oh, I'm sorry, you're right, you're right, here it is. So we're coming up to 170-4, so it's around here, right? Because our length of grade is 2, here's our 1-78-4, which is this line, so we come up to here. So we can come over here. Do we know the velocity that gives the velocity?
Yeah, it's 2.
It's 2.
So it goes off the chart, it's automatically at 1.
Yes, it goes off the chart because it's over here. We come down and we know it's 100% efficient. So RF is equal to 1.0. Okay? And that's what they told us here. So RS, we can either figure it out, we can figure that out. I have to flip this over to find out what RS is. I'm a mess here, I'm sorry.
Yes,
But, you said RS is that, RS is right there. So RS, this is the equation right here. So it's K sub U, your velocity, your cross slope, and your length. And that's what we've done here. Here. And with RS, if we work it out, we get 0.15. So then the efficiency is 1 times 0.54, which is this gutter flow ratio, plus the RS times 1 minus the 0.54 is equal to 0.61. And that is this equation right here. Okay? Here. Okay? And then the Q intercepted is just equal to the efficiency times Q. And that's what we have, our efficiency is 0.61 times our Q. So our Q intercepted is 0.80 CFS. And so we can figure out our bypass flow because we know our gutter capacity is 1.31 minus what we intercepted. So the bypass is basically 0.51 CFS with 0.5. So you can run through all that again with a 4-foot long grate. The efficiency there was 0.76. The intercepted was 1 CFS, and so we had a bypass flow of 0.31. Okay? And that brings us up to so sorry, no, that was so complete. Oh, I did it. So now what we have to do is this little review. Can you name hydraulically efficient and bicycle-safe grates? Curve vane, I heard that one.
50 by 100.
50 50 by 100, yep. Any others? Tilt bars, right? Tilt bars at 45 degrees and 30 degrees. The P30, those are the narrow bars that it also had space. So, list variables that affect the grade efficiency.
Oh, yeah.
Length, width, well, length, does length affect efficiency?
Not very much.
Not very much. Width does, right? Because you want your grate to be as wide as the frontal flow, and then you get pretty good efficiency, that helps.
What style of grate you have?
Yeah, the type of grate you have.
Parallel bars.
Yep, the type of grate. The slope, what kind of slopes?
Low slope.
Cross slope and longitudinal, yeah.
Almost.
And you also want that ratio, the gutter flow ratio, frontal flow to total flow. So what is frontal flow?
Basically, the flow to the
It's a frontal flow to the total flow. So gutter flow is different from frontal flow. Frontal flow is the frontal flow intercepted to the total frontal. And side flow, side flow interception. Yeah, it's kind of like what it says, it's the percent of side flow that's intercepted. And can you give me the procedure to calculate the hydraulic capacity of a grate? Is that Q intercepted equals what?
QCW?
It's efficiency times the total flow. So it's just E times Q. And to find the efficiency, you kind of go backwards and you find your RF and your RS. And then you can find
Then tomorrow, can you have the solution for that last problem we did on the board, so we can, like, I didn't have time to copy it all down. Thank you.
Okay, well, it's 4 o'clock, so thanks a lot, guys, for your patience.